Hey everyone, thanks for joining us. My name is Suha, and I'm joined by Carson, Evan, and Jim. In this talk, we'll discuss the underhanded antics that can occur simply from loading an untrusted pickle file or machine learning model. In the process, we'll introduce a new tool, Fickling, that can help you reverse engineer, test, and even create malicious pickle files. If you're a machine learning practitioner, you'll learn about the security risks inherent in standard machine learning practices. If you're a security engineer, you'll learn about a new tool that can help you construct and forensically examine pickle files. Either way, by the end of this talk, pickling will hopefully leave a sour taste in your mouth.
So what is pickling? Python pickles are compiled programs that run in a unique virtual machine called a pickle machine, or PM for short. The pickle machine interprets the pickle file sequence of opcodes to construct an arbitrarily complex Python object. The pickle format is a streaming format, which allows the pickle machine to incrementally build the resulting object as portions of the pickle are downloaded over the network or read from a file. The pickle machine uses a Harvard architecture, which segregates program opcodes from writable memory. This architecture prevents pickle files from containing self-modifying code and memory corruption bugs. The pickle machine's architecture also lacks support for conditionals, looping, and even arithmetic. During unpickling, the pickle machine reads in a pickle program, executes all of the instructions, and at the end, whatever object is at the top of the stack is returned as the deserialized object. From this description, one might reasonably conclude that the pickle machine is not Turing complete. How could this format possibly be unsafe? Pickling is one of the most popular ways to serialize and deserialize data in Python. A major reason why pickling is so popular is because it is shipped with Python. On the left is an example of how you would pickle objects. Here you can see that I create a list, a dict, and an instance of a custom class and serialize them to the pickle file example.p. Simply import the pickle module and you can serialize whatever Python object you want to a file. Wonderful. On the right is an example of saving a model in Pytorch. First, you create your neural network and then you save the model. Saving the model in Pytorch is equivalent to opening and dumping to a pickle file, like on the left-hand side. Pytorch does save additional information packaged in a zip file, but the pickle files containing the models are the most interesting to us. As we said earlier, a pickle file is essentially a program with its own instruction set that is executed within the pickle virtual machine. This is a decoded pickle file. The pickle instructions, such as global, put, mark, reduce, etc., describe to Python how to deserialize the encoded object. This is the decompiled version of the pickle file as Python code. In this case, you can see it calls eval. The result of the call to eval is on the top of the stack, which in this case, the value is none. In general, you can modify these pickle files to do whatever you want. You can inject individual functions like eval and exec. You can inject and create your own objects, and you can modify existing objects from a pickle file. This decompiled output is a sneak peek of some functionality built into our tool, Fickling, which we'll be showing off more later. We should all know this by now, but there's no secure way to deserialize untrusted pickle files. The pickle machine contains two opcodes that can execute arbitrary Python code outside of the pickle machine. These opcodes are global and reduce. Global is used to import a Python modular class, and reduce is used to apply a set of arguments to a callable, typically previously imported through a global. So in the example on the last slide, we called eval using global to get access to the eval function and reduce to apply eval to a string. Even if a pickle file does not use reduce, the act of importing a module alone can and will execute arbitrary code in that module, so global alone is dangerous. The problem is that the global opcode is required for deserializing custom objects like machine learning models. So if one were to completely forbid the global opcode, then there would be no advantage of using Pickle over a standard alternative like JSON, CBOR, or protobufs.
So you may have figured this out by this point, but the majority of machine learning frameworks still use pickling, despite all of this knowledge of the potential dangers of pickling. And worse yet, machine learning models are freely and anonymously shared online. But it makes sense that people would find this convenient. Pre-trained models are typically treated as free byproducts of machine learning, since they allow the valuable intellectual property like algorithms and corpora that produce the model to remain private. This gives many people the confidence to share their models over the internet, particularly for reusable computer vision and natural language processing classifiers. Websites like Pytorch Hub facilitate model sharing, and some libraries even provide APIs to download models from GitHub repositories automatically. The risks of using pickling in the machine learning ecosystem seems to be well known, at least in the security community. Yet there isn't a clear path forward in making the system more secure. So to help improve the overall security of the machine learning ecosystem and provide computer security researchers with a new tool to forensically analyze pickle files, we've developed a new tool and library called Fickling that can be used both to inject arbitrary code into existing pickle files, as well as to statically analyze pickles for certain classes of malice. Noting, however, that in the general case, proving whether a given pickle file is malicious is, of course, undecidable. Fickling has its own implementation of the Pickle Virtual Machine, or PM, and it's safe to run on potentially malicious files because it symbolically executes code rather than overtly executing it. Fickling can not only disassemble and emulate pickle files, it can also decompile the opcodes into equivalent human-readable Python code. It also provides an API for rewriting pickle files, including injecting arbitrary code. Fickling is open source, and you can try it right now.
Thanks, Evan. So we can use Fickling to develop exploits for many different scenarios in which anonymously shared pickle files can be an attack vector. Now, whether or not these scenarios apply to you and your system is a matter of threat modeling. Often, ML models are trained from private proprietary data or in a novel proprietary way. To leverage that, a malicious pickle file can secretly include Python code to exfiltrate all local files to an external server. Denial of service type attacks are also possible. One could introduce arbitrary delays or break the model itself altogether. There's also an entire area of ML research about more algorithmic attacks like backdoors and poisoning attacks that all become much more feasible to exploit with pickles. What's more, all of these attacks can be targeted to particular users by leveraging the target's local time zone or IP address. Now let's dive into some demos. First, I'm going to show you a small example of the Fickling CLI, and then we'll move on to some more ML-specific ones. Let's start by pickling a very small list of numbers. Now we can load it into Fickling. One cool feature of Fickling is that we can trace through the opcode sequence of a file, as we're doing right now. Another fun feature is that Fickling can detect any overtly unsafe code in your pickles. But this feature should not be relied on in lieu of actual security practices. Now, let's use Fickling's binary rewriting feature to inject a print statement into the pickle. All right, so we're moving it into a different pickle. Let's see if it worked. And there we have it. We've just injected arbitrary code into this pickle. Let's see if Fickling's safety feature can detect this. And it can. So if you visit the Fickling repository, you'll notice that there's multiple examples of Fickling in practice. The Pytorch poc.py file contains a program that injects a payload into a Pytorch model that will then exfiltrate your local files. Now, the particular proof of concept is rather lengthy, so let's just take a look at the output. So as you can see, multiple zip files were created, and when the model was loaded, the local files were exfiltrated. The next proof of concept is contained in the NumPy POC file. Now, this example is a lot simpler. It was adapted from the proof of concept for CVE 2019-6446. That CVE showed that numpy.load is vulnerable to arbitrary code execution, since it allowed pickle by default. So first we created this test class, but inside of the reduce method, it contains a command that will actually run the previous proof of concept. We're going to showcase the different behavior between loading it with pure pickling and loading it with Fickling, and see whether or not Fickling can determine if it's safe. As you can see, the exfiltration occurs with Pickling, but not with Fickling, and Fickling static analyzer determined it to not be likely safe. This next proof of concept is called the Inject MobileNet proof of concept, and it's my personal favorite. So we started off by loading the MobileNet v2 model from Torch Vision. Then it runs the eval method. So the eval function method traditionally pushes an ML model from the training phase to the inference phase. However, we use Fickling to inject a payload that overrides this method with our own custom Python statement, as you can see here. Now let's try to run this file. So as you can see, nothing was printed during the first execution of eval, but during the second, this statement, we can run whatever custom Python code we want to was. Now, obviously, you can be as creative as you want here with what custom codes in the machine learning model to override and what Python statements you want to execute in lieu of that. This next proof of concept is contained in the faultinjection.py file. This one's a bit more complex, and I won't dive into the source code for the sake of time, but I will show you the output. We use this tool called Pytorchify, that's Pytorch FI, that perturbs the weights of a neural net to inject a fault. It allows us to force a neural network to misclassify an image. Now, Fickling does mark this as unsafe behavior, but as I stated before, that's not a substitute for genuine safety checks. I used Fickling to check if the AST properties and the ASTs match here, but that's likely not the best check for your use case. And what the best checks are is something you should look into after threat modeling.
While we were developing our tool Fickling, we decided to investigate existing threats in the ecosystem, and that's when we became aware of Pytorch Hub. Now remember, this is a service for distributing pre-trained models from anonymous sources using Pickling. Once we were aware of Pytorch Hub, we reached out to them to express our concerns and advocate for a safer mechanism for distributing their models. Unfortunately, Pytorch indicated that they do not plan to adjust their distribution process, but they will continue to vet their users who publish models. Now, Pytorch Hub, of course, is not the only vulnerable tool or framework out there. Scikit-learn describes their security limitations here in this screenshot, recommending different metadata that should be saved alongside the pickled models. You'll see similar observations to this in the documentation for other frameworks and tools out there. However, how frequently are these best practices actually followed? Proper security procedures should not be relegated to best practices, but rather they should be the defaults. We can't assume that users will go out of their way to increase their security, and so we have to do it for them. Now, if you're a member of the ML community, you might be wondering what are the other options you have to use instead of Pickling. If you absolutely must continue to use Pickle, you can use Fickling for safer unpickling of your files. As you saw in our demo, Fickling will attempt to detect potentially malicious code inside of your Pickle files without actually having to execute the file itself. Besides that, many different ML platforms will openly acknowledge the risk of using Pickle, and they will offer you safer recommendations, as we saw in the previous slide. As another example, you can see the use of state dict and load state dict in Pytorch. But now, if possible, you should really be using another safer file format for storing your models, like ONNX or HCF5. The downside is, and this is why Pickling became so common in the first place, is that these formats won't work for you out of the box, as they'll require custom serialization to be built to serialize your model. Ideally, different ML frameworks could dedicate time to making their common models more serializable into these safer formats, hopefully encouraging users to avoid using Pickling altogether.
Thanks, Jim. So much research has been dedicated to novel machine learning attacks like model inversion and extraction. And there's plenty of tools that can help you ascertain your risk with them, like Microsoft's Counterfeit, Privacy Raven, IBM ART, and Pytorch Hub. But these shouldn't be the only focus of machine learning security. I highly recommend reading the paper Summoning Demons. So these researchers demonstrated that implementation bugs in libraries like heap corruption can enable much more powerful adversarial evasion attacks. So as discussed in the paper, we can think of these novel ML attacks as demons, but these demons are summoned by vulnerabilities in our tooling. For instance, in our Pytorchify demo, the vulnerability of pickle files summoned the demon of default injection. So the Atlas matrix from MITRE is a pretty good starting point for thinking about how these vulnerabilities and attacks fit together. Now, pickle files are just one issue in the large, complex machine learning ecosystem. And as we discussed earlier, attacking pickle files isn't a concept specific to machine learning. Bottom line is we need to learn from other areas of security. First, we need to make our tools and frameworks as secure as possible by default. This issue has plagued systems of all forms, and the recurring lesson is that most people will not go out of their way to make their system more secure. So we should recommend it for them. Second, we should limit access to model files, and when they're distributed, sign and verify files from unknown sources. Sharing and receiving files from unknown sources has become commonplace in many applications, and so should be their protections. Lastly, there seems to be a tendency to treat ML models as standalone objects, but we need to treat ML models more like standard software. So that means we should have better management of model life cycles. We should have better monitoring for detecting and triaging attacks. And we need to assume inputs can be adversarial, so we need better validation of inputs. And we also need better testing to prevent security bugs. So pickling is a convenient serialization method, as it does allow you to save arbitrary objects. It makes sense why choosing pickling for persistence is a popular practice amongst Python programmers and ML practitioners. But unfortunately, pickling is very unsafe and represents a serious supply chain risk to the ML community. We should be more security conscious, and we need to make our tools secure by default. And that starts with not making pickling our default model serialization. We hope you enjoyed our over-the-top pickle puns, and please let us know if you have any questions. So Trilobits runs a Slack channel called Empire Hacking, where we talk about various security topics. Feel free to get in touch with us on the Empire Hacking Slack, and make sure to check out Pickling at the GitHub link here. We also have a blog post accompanying this presentation with more technical details. Thank you all for your time.